Welcome to this second TVB showcase. Today we will focus on how to simulate seizure-like events or epilepsy within our virtual brain environment. Therefore, we will have a look at this article called On the Nature of Seizure Dynamics. The authors in this article describe their new local model called the Epileptor. This model consists out of 5 differential equations, which can be seen here. So one, we have this slow permittivity variable z, which acts on a slow time scale, and then we have x1, x2, y1, and y2 acting on a fast subsystem. They will create those fast oscillation and spike wave events which can be seen in seizures. This dynamical system basically has 2 bifurcations, which are drawn here in this graph on the right side. One is the saddle node bifurcation up here, where we have a stable fixed point, an unstable fixed point, and a limit cycle within our phase space. And the saddle node bifurcation is basically those 2 fixed points approaching each other, colliding, and then leaving all trajectories flowing onto the limit cycle. The other bifurcation is the homoclinic bifurcation, where this unstable fixed point will collide with the limit cycle, leaving all trajectories flowing onto the stable fixed point. So here in figure 5 we can see how this looks like in a 3-dimensional phase space and also the time series. So in panel A of figure 5 we can see the simulated seizure-like event, and in panel B we have the time series of empirical data. On the right side you can see the 3-dimensional phase space, and as we said, we have those fast oscillations on this limit cycle, and during those oscillations this variable z will increase until a certain point where we have this homoclinic bifurcation and the system will jump into the stable fixed point, and here z decreases again to a certain point where we have this saddle node bifurcation and the system will jump back into the seizure state. On the left side you can see the time series of the simulated seizure, where we have those pre and post-ictal time periods, and within we have those fast oscillations. And you can see the red line represents this variable z, and seizure onset is at its lowest point and seizure offset at the highest point. Down here this is the empirical data where the phase space looks very similar, and you can see here the slow variables are biological recordings of biological metrics. So now we will have a look at how this can be recreated within the virtual brain. Therefore we switch to the simulator page, and up here we select the phase plane viewer. We will select our model called the Epileptor, and we also want to increase the integration step size. And on the right side we have the 2-dimensional representation of our phase space, so a phase plane, and you can see those 2 null lines intersecting 3 times, generating a stable fixed point down here. So if we start somewhere in the near of it, the trajectories will always flow to the stable fixed point and stay there. We have here an unstable fixed point, so trajectories won't flow to that direction, and up here we have this limit cycle, so if we start anywhere here near this, we will have those fast oscillations. And as we said, we have 2 bifurcations. One is the homoclinic bifurcation, and this happens when we increase z. We will see the limit cycle breaking up and all trajectories flowing onto the stable fixed point down here. And the other one is the saddle node bifurcations, where the 2 fixed points collide, leaving all trajectories flowing onto the limit cycle. So now even if we start down here, you would see those oscillations. Okay, this was a first introduction to the Epileptor, and in the next video we will see how we can incorporate this into our brain network model and create seizure events in a large scale. Thank you for listening, and see you next time.